I'm going to go ahead and introduce today's presenter. Autumn Phillips is an R&D chemist here at Inorganic Ventures. She has experience with bulk scale manufacturing, reaction and purification performance and improvement. She also has several years of experience in the manufacturing of custom CRM products. Autumn has received a Bachelor of Science in Biochemistry and a Bachelor of Arts in Chemistry from Virginia Tech. Without further ado, we're going to go ahead and kick off the presentation. I appreciate you all for joining us this morning. Thank you so much.
Hello everyone, and thank you for joining us. In this presentation, we'll be going through some quick tips for working with tin and mercury. So for this presentation, we're going to be specifically focusing on issues related to ICP analysis of tin and mercury. So the first element we're going to focus on is mercury. Mercury is definitely one of the problem elements. Chances are, if you've worked with mercury and analyzing mercury, you've run into some type of issue along the way. So some of the more common methods for analyzing mercury are some EPA methods, as well as pharmaceutical applications, so USP 232 and ICH Q3D. Both require mercury testing. But the main thing to focus on is that mercury must be in the +2 ion form to get accurate results with ICP analysis. So how do we keep mercury in the +2 form? Well, the first thing you want to do is you want to avoid neutral or basic media. This can cause formation of the insoluble carbonate. You also want to avoid mixing with tartrate, because tartrate will reduce mercury to the metallic form, which is volatile and can cause loss of your analyte. One thing that we use at Inorganic Ventures is we use tartrate for stabilizing antimony. So we have to make sure and be careful that if we have a standard that contains both mercury and antimony, that we're using antimony stabilized with HF instead of tartaric acid. So another thing to watch out for is that reducing environments can convert the mercury 2+ ion to the dimer, which is mercury 2+, or all the way down to the metallic form. So the issue with having the dimer in your solution is that the dimer will actually disproportionate in the presence of chloride or some other ligand into metallic mercury and the mercury 2+ ion. So again, metallic mercury is volatile and is going to cause issues with either loss of mercury over time or issues when analyzing your standard on the ICP. Another thing that can convert the ions to the dimer form is leftover nitrogen dioxide fumes from your reaction or digestion process. So if you have those fumes left over in the container and they're allowed to sit with your mercury solution, that can cause formation of the dimer. So the way that you get rid of this issue and convert the dimer back to the mercury 2+ ions is you can boil your standard with excess nitric acid. So we do this a lot if we have standards that are older, that are more than a year old. We'll go ahead and be on the safe side to make sure we don't have that dimer present. We'll go ahead and boil those with excess nitric acid. The only thing you need to keep in mind for this, though, is that if you do go this route with boiling with nitric acid, you may have to recertify your standard to get an accurate concentration. So what matrix should you have your mercury standards in? So a lot of people like to use nitric acid as the matrix for their standards, but there are issues for mercury in nitric acid alone. So in nitric alone, mercury can adsorb to the container walls of plastic. We found that about 1 ppm is adsorbed. So one way that you can mitigate this is you can keep your standards in borosilicate glass instead of in plastic. But this does cause some additional concerns as well. If you have HF in your standards, they can't be contained in glass because the HF is going to be caustic to the glass. Another thing is that borosilicate glass contributes a much higher level of contamination than plastics, LDPE or HDPE. So if you have some of these analytes listed here at the bottom at low levels in your sample or your standards, this may cause an issue because glass is going to contribute some of these as contaminants. So another option for stabilizing your mercury and nitric acid without using glass containers is you can stabilize with 1 ppm gold trichloride. So we have a link to the EPA bulletin that recommends this here. Inorganic Ventures does sell a 1000 ppm gold standard in nitric acid, but just be aware that this does still contain chloride, as the starting material is still gold trichloride. So this still may cause some interference issues if you're looking at arsenic or selenium on mass spec from the chloride. But since it is such a low level of chloride, if you just add that 1 ppm gold to the matrix of your blanks, standards, and samples, this should account for any interference issues that you potentially may see. There are also methods that we've heard of for stabilizing mercury alternatively with L-cysteine in nitric acid. We've linked the paper here just for your reference if you want to go through and see if that may be an option for you. Again, we haven't used this method in-house though, so we haven't personally had any experience using this, but we have heard that this is a good option as well. We think that the best option for stabilizing mercury in your solutions is with HCl in the matrix. So hydrochloric acid is going to stabilize the mercury, and you're going to be able to store your standards in plastic. You won't require glass because the mercury is not going to stick to the plastic surfaces in a hydrochloric acid matrix. So you can have a pretty low level of hydrochloric acid and have your standards still remain stable depending on the concentration. So if you have low level mercury, 1 to 2% hydrochloric acid should be sufficient for stability. So some concerns for using an HCl matrix though, again, there is that chloride interference for arsenic and selenium if you're analyzing those on mass spec. So we recommend using helium mode or the collision cell to break up these interferences if you are analyzing those two elements. So another concern is that if you do have that dimer present and you add the chloride, that chloride is going to cause precipitation of the mercury or disproportionation of the dimer into the metallic form. So you want to make sure that if you think you may have the dimer present or there's a potential it could be present, you do boil that with excess nitric prior to adding your hydrochloric acid, and then you should be fine. Another concern is if you're having silver in your standards or your samples. Silver will precipitate with trace chloride. So if you do have silver, you want to make sure that you have an excess of chloride to stabilize the silver. So anything 10 ppm or less of silver can be stabilized pretty well in 10% hydrochloric acid, but higher concentrations are going to require a larger hydrochloric acid concentration. So if you have any questions about that, definitely reach out to our technical team. We can give you some assistance there. But just be aware that if you do have silver and chloride in your standards or your samples, they're going to be photosensitive. So you need to make sure to keep those away from light to avoid formation of that solid silver chloride. Another analyte to look out for if you're using a hydrochloric acid matrix is thallium. So in chloride, thallium must be in the +3 state, as the +1 can precipitate out as the thallium chloride. So if you are ordering your standards from us and you are analyzing thallium and it's going to be mixed with hydrochloric acid at some point for your standards, just make sure to mention that when you request the standard from us, and we can add the condition to use thallium-3 instead of thallium-1 because thallium-1 is the normal thallium concentrate that we would use. So when you run your mercury solutions on your ICP, there are several things that you want to look out for. So again, mercury does stick to plastic if it's in a nitric acid matrix alone. So a lot of your instrument introductory components are going to be made of plastic. So we do recommend using a glass intro system if possible. With the plastic issues, your initial analysis is probably not going to be affected, but you will have sticking, especially in that PVC tubing if you're using a peristaltic pump. You will have memory effects and washout issues for mercury, so just keep that in mind. So we recommend using thiourea or higher hydrochloric acid rinses to help get rid of the mercury. So another issue for analyzing mercury on ICP is again that the dimer can be converted to the metallic form and the mercury 2+ ion in the presence of chloride or other ligands. So again, same thing with boiling with nitric acid prior to adding any chloride or other types of ligands or anything that's going to reduce that, that dimer down to the metallic form. So even if there's just a very small amount of that metallic mercury present, you are going to get way higher signal from that mercury in your instrument just due to that really high transport efficiency of the mercury to the plasma because that metallic species is so volatile. So if you're seeing really, really high recoveries, you can probably guess that the mercury species has been reduced to the metallic form, and that's what you're seeing in your results. On the other hand, if you're getting low results, a common issue is you had adsorption of the mercury species to your containers at some point. So whether that be the bottle itself or your pipette tips, whatever the case may be, if you do have nitric acid as your matrix, that mercury could have stuck to something along the way and caused loss of your analyte. Also, if you had precipitation of the mercury as the metallic species, and those are some older standards, you may have already lost the mercury due to volatility, and that could also be a reason that you're seeing those low results in your instrument. So the rinse solutions we recommend for mercury is 1 to 10% hydrochloric acid along with 0.5% weight to volume thiourea. This has worked really well for us for getting mercury to purge out of our system, and this also works really well for gold. So if you need a basic rinse, we can also use ammonium hydroxide at 1 to 5%, and that's for both OES and mass spec. So that brings us to our tin analysis. So the primary issues for analyzing tin are volatility of the chloride species and the tendency to hydrolyze. So when tin hydrolyzes out of solution, it forms a semi-colloidal suspension, which is tin 4-hydroxide. So poor recoveries for tin can generally just be attributed to either incomplete sample digestion or instability in the digested sample. In solution, tin forms tin 4 and tin 2, which both form complex ions. So tin 4 hydrolyzes much more readily than tin 2. So tin 4 is really going to be your issue for stability in solution. So when tin is digested in hydrochloric acid, you're first going to form the chloride with the tin 2, but over time, air can easily oxidize the tin to the +4 ionic form, and this is going to cause issues for hydrolysis later on down the road. So it does require a large excess of chloride to stabilize the tin, and again, over time, you will still have issues eventually if you don't keep an eye on the chloride levels in your tin to make sure that you have enough there to keep your tin in solution. Tin is not going to be stable in a nitric matrix alone because it will oxidize to the insoluble stannic oxide, which is very insoluble and resistant to all types of acids, even hydrofluoric acid, and it's actually going to require a fusion to get that back into solution. Another type of matrix to avoid is basic media. So tin is not going to be stable in basic conditions. It's going to fall out as insoluble hydroxides or sulfides. Organic tin compounds are going to actually adsorb to sediments. So if you're analyzing tin content in some type of natural water system, the majority of that tin is going to be found in the sediment along the bottom of that water system. So again, tin can be stabilized in hydrochloric acid alone, but it's going to need a large excess. So the age of that solution is going to matter, as oxidation can occur over time and cause issues with the ratio of tin forms in your solution. So the best option for keeping tin in solution is to just stabilize with a little bit of HF. The hydrofluoric acid is going to fix the tin in solution and prevent any type of hydrolysis or oxidation from occurring. This brings us to analyzing your tin samples on your ICP. So as we mentioned, tin is going to be best stabilized in hydrofluoric acid. However, HF is caustic to glass components, which many intro systems are composed of. So if you have an HF resistant system, you can go ahead and run those samples as long as your HF content is low enough to not degrade those components. However, if you do not have an HF resistant system, we recommend neutralizing your HF with triethanolamine prior to running your samples and standards on the instrument. So T just needs to be in a slight excess, so just bring it to a neutral pH of 7 to 8. And it's important to mention that the fluoride ion itself is not caustic to glass, is not going to attack the glass. It's HF itself that is going to cause your issues. We do want to mention, though, that if you are analyzing mercury in any of your following procedures after analyzing any solution neutralized with T, you do want to make sure and switch out your wash solution prior to that mercury analysis, because we found that the T can actually reduce the mercury and cause that to come back up through your lines back into your system. So you want to make sure that you remove that and you're not reducing your mercury once it makes it to the wash solution. If tin is being stabilized in hydrochloric acid alone, same as we saw for mercury, that chloride can cause issues on your mass spec for analyzing arsenic and selenium. So just make sure you're using that helium mode or the collision cell to break up those interferences. Another issue is that tin or stannic chloride can cause a vaporization interference. So you're going to have higher vapor pressure, which causes higher transport efficiency to the plasma, and you're going to get higher results than expected for tin. So this is really going to be an issue if you have different ratios of tin-2 and tin-4 in your samples and standards. So if you have a higher ratio of tin-4 in your standards than in your sample, you're going to get low results because you're expecting to see a higher signal than you're going to get if you have more tin-2. So again, it's best to fix the tin in solution with a small amount of hydrofluoric acid to keep these species in solution. The last issue that I wanted to go through is the hydrolysis issue, so the formation of tin-4 hydroxide. It's going to form a very fine semicolloidal suspension that's actually really hard to see. So you just want to make sure that if you do have tin solutions stabilized in hydrochloric acid alone, that you check and make sure that those are crystal clear prior to analysis, making sure that you don't see any of that very fine white suspension. And it's important to note that particulate that is less than 8 microns can actually make it to the plasma. So if you do have this type of suspension in there, you can check for that by running it through a micron filter. So it's going to break up the semicolloidal suspension, and it's going to allow you to see varying amounts of tin because it's going to break it up and allow it to go through the system. So you can tell if you have any present if you see some low or sporadic results from running your samples. So again, if you just add a little bit of HF, it's going to bring your tin back into solution and fix any of these issues that you're seeing. So lastly, we're going to talk about which rinse solutions you want to use for tin. So we don't really see a whole lot of sticking in ICP OES. It's really more of an issue for mass spec. So we recommend starting out with a 10 to 20% hydrochloric acid rinse solution. So a pretty high hydrochloric acid is going to be required to rinse out your tin. If you are adding HF to your rinse solution, this will help purge the tin from the system, but you do want to make sure that you're not running a higher HF content than is appropriate for your instrument. So 0.1 to 2% is probably the highest you want to go for OES, 0.05 to 0.5% for mass spec, so you really don't want to go very high at all in your HF content for rinse solutions on mass spec. We don't recommend running anything higher than 0.2% if you have a glass nebulizer or spray chamber. This is going to cause issues for your boron and silicon results. And if you do have an HF resistant system, we still don't recommend going over 3% hydrofluoric acid because this is going to degrade your coating on your instrument components. Lastly, if you're really just seeing a lot of washout issues, we recommend replacing the tubing, as that PVC tubing is going to be the primary place where you're going to have sticking. So that concludes our quick tips for mercury and tin analysis, but we do have a webinar available on our website. If you go to the Education tab and Technical Videos, that webinar is called Aggravations in the Lab, Solving Troubles with Tin and Mercury, and that goes a little bit more in depth into some issues that we see for tin and mercury analysis on a daily basis. That concludes this presentation. Please submit any questions you may have and we'll be glad to answer them.
All right, thank you, Autumn. And thank you, everyone. We have some questions that are starting to come in. So again, if you have any questions you'd like to ask, please feel free to submit them through the Q&A function that should be at the bottom of your screen. So with that, we'll go ahead and get started with the first question. Autumn, this question is coming in and it says, for rinsing out mercury, the rinse you recommend is a mix of HCl and thiourea. Would thiourea alone be sufficient? The reason they ask is they need to avoid trace hydrochloric acid due to an interference that's going to form in their hydrogen reaction cell.
Yeah, so we've always used it in conjunction with hydrochloric acid. We haven't tried rinsing it with thiourea alone, but you could definitely give it a try and see if that helps. Or you could try using ammonium hydroxide as a rinse to get it out if you want to avoid the chloride. But yeah, I would definitely give it a try, but I can't speak to whether or not it will work or not without the hydrochloric. But yeah, if you can use a basic rinse, you might want to try ammonium hydroxide instead.
Great, thank you. All right, the next question is, will rinsing the ICP system with nitric acid cause a mercury memory effect as well?
Yeah, it definitely could cause issues because running the nitric through your system is going to cause the mercury to stick to any plastic components that it's encountering as it goes through. So if any of your connectors or anything that it's touching or your tubing is plastic, then it could definitely cause some sticking issues. So I would try to avoid nitric acid as the rinse if you can, or definitely have some hydrochloric added in with it to try and make sure you're not causing those issues.
Great. All right. The next question we have is a small amount of HF is approximately what ppm or what percentage? I think this came in before your last slide, but if you want to go ahead and yeah.
Yeah, so we normally would recommend at least trace HF, and at IV we normally call 0.2% volume to volume trace. So I would try starting out with 0.2% by volume HF, and that should prevent any issues with the 10.
All right. The next question is, what challenges could I have using tin chloride instead of sodium borohydrate as a reducing agent?
That I'm not too sure about, just because that's not something that we've used in-house, so I'm not really sure how those would compare. But I would imagine you'd have similar issues to what we have with hydrochloric in needing a large excess of the reducing agent, whatever that may be, to make sure that it's enough to stabilize your tin. But like I said, I don't have any personal experience with that.
All right.
Yeah, I would just try to add a large excess if you can, and just make sure you do checks frequently to make sure that it's stable, and maybe start an in-house stability assessment of those, and just check versus a new prep to make sure that you're not losing any tin over time.
All right. Perfect. So the next question is, I think more with compatibility. Will adding HF for tin affect the mercury analysis? And how much HF should be added?
Yeah, so again, just a trace amount of HF, 0.2% by volume should be enough to stabilize your tin. Even at higher concentrations, it only takes a small amount. And it shouldn't affect your mercury results. You should be able to have HF in the matrix with mercury and not cause any stability issues. The only thing that you will have to keep in mind is that if you do have mercury, you will have to add some hydrochloric acid to keep it in solution, because if you have HF, you can't have it in the glass bottles or glass containers. So that's the only thing that I would make sure to keep in mind for that.
All right. Okay, the next one is we are having linearity issues with our tin curves ranging from 0.04 to 1 ppb curving down. We are using the apex and have 2% nitric, 1% hydrochloric acid, and a 0.25% HF acid matrix. Do you have any suggestions to help with linearity? We need to prepare the calibration standards by first adding hydrofluoric, then HCl and nitric, instead of directly diluting down with an already prepared matrix. Any thoughts on that one, Autumn?
I would think that matrix would be good to just dilute directly with it if your HF is already in the matrix. But like you said, the only thing I could think to try with that would be to spike in the HF first. Depending on what other elements are in there, you may have issues if they have instability issues with higher concentrations of HF. But yeah, that's what I would recommend is spiking in the HF first and then adding the rest of your matrix in second to see if that helps. Yeah, I'm not sure. I haven't seen a lot of issues like that. Do you have any suggestions for that, Mike? Or
no, I think that you've pretty much hit it. Yeah, with that sort of, anytime you see the calibration curve, sort of start to level out or slope down at the end, usually for us that means that we've hit sort of the concentration limit for the detector. But at that concentration range that they've listed, I can't imagine that would be a possibility. I would add that if they are having issues with that and they continue to have issues, to contact our technical support team, so that way they can send a little bit more information and data directly to our team, and we can sort of review that and send it to some of our chemists to have them take a look. That's a service that we have available for, everyone to take advantage of.
Yeah, definitely.
All right. Next one, and I do apologize. This is my fault. The first link that we sent out to register for receiving the sample prep guides did not work. There is a new link in the chat. So you should be able to register for those by using the newest link that was submitted to the chat. All right. Next question is, how would we expect a novice with no background in analytical chemistry, say like starting off in a cannabis testing lab, to remember all this information if they're just if they're not really experienced in these chemistry issues?
Yeah, we have a lot of really good resources on our website that you can print out or refer to as needed. We have the ICP operations guide, which gives a lot of good tips for ICP in general. We also have our sample preparation guide. So if you're working with specific elements, obviously, or if you are having issues with a particular element, I would definitely refer to the sample prep guide or the ICP operations guide. Our interactive periodic table is really helpful too. That one gives just some really quick basic information. If you go to our website, it's under the education tab and then interactive periodic table. You can click on any of the elements and get some quick information there. So that might be a little more helpful if you're just looking for, something really quick. But definitely take advantage of those technical resources on our website, because those can be really helpful with helping you solve some of those problems. But yeah, it is a lot to remember, and certainly I wouldn't expect anyone to remember it right offhand, but we do have those resources that you can refer to anytime.
Yeah, that's exactly what I was going to say as well, Autumn. Our website has an excellent resource section with links to various other sources as well. And also a great technical forum for people to submit questions as well. And it can be very difficult starting out, but if you have a good place to start, we can definitely help find you answers that you may need, because it is certainly complicated. So webinars like this and any trainings, conferences, any resources you can pick up will definitely help you in your analytical chemistry journey. All right. So a little bit of an update to the thiourea washout. Steve Pappas has written in. He's joined us for multiple webinars this year. And he has said that thiourea alone will definitely work for mercury rinse out. So thank you for that, Steve.
Awesome.
And the next question is, the last time I tried thiourea, I had problems with arsenic recovery. Have you had this problem yourself, and how would you deal with that?
We have not ran into any issues with thiourea causing arsenic results to be low. But if you're using mass spec, maybe use the collision cell or helium or hydrogen mode if it's causing any type of interferences for arsenic. But that would be my main suggestion. I'm not sure if they mentioned using OES or mass spec, but try using collision cell.
Mm-hmm. You could also try to have an extra rinse method in there to try to rinse the thiourea out as well, if that's definitely causing an issue. Just extra rinses may help. With something directly after the thiourea would be my only other recommendation. Yeah. All right. Next question. With mercury, I've been told that 0.1% of HCl would still work in keeping the mercury in solution. Does that sound right to you? As they want to minimize hydrochloric acid due to low level mercury, but they want to try to get most of it brought into solution, obviously.
Yeah. Depending on the level of mercury that you have in your standards, that may be enough. We tend to go on the safer side with higher hydrochloric just because we're looking for long-term stability of 5 years. But depending on how long you need it to be stable for too, it may be stable for, at least long enough to run your analysis. But I would try it and then again, just check for stability depending on how long you need that standard to be stable for, just to make sure that it's not, having issues over time.
Great. All right. So we are winding down the last few questions here. What matrix would you recommend for a thiourea rinse? Could you use an HCl matrix?
Yeah, that's what we normally use for the thiourea. If we're running it on OES, it's usually a 5% hydrochloric and 0.5 weight to volume thiourea. Or for mass spec, it would be a 2% hydrochloric. So yeah, you can definitely use HCl for your matrix with thiourea.
Great. All right. Next question is, do the recommendations for mercury analysis still apply for analyzing mercury and sulfuric acid as opposed to nitric or HCl? Do you have any additional suggestions for mercury and sulfuric?
Yeah, the same sort of issues or principles would apply for an analysis of mercury and sulfuric acid. I don't really have any additional suggestions just because it's not really a common matrix that we would analyze with mercury. Yeah, I'm not sure. Do you know of anything like that?
Yeah, it's not really a common matrix for us. So I'm not remembering anything off the top of my head. But if you're having issues with it, again, I would recommend reaching out to our technical team. And we can definitely look more in depth into it. Since it's not really that common of a matrix for us, I'm having a little bit of trouble recalling if there'd be any issues or not. All right. Last question is, will the slides for this seminar be available for download? I am actually going to ask our administrator to jump on. I know that the webinar recording itself will be posted, but I don't know if the slides are available for download.
Yeah, Mike, when they go to that technical videos page on our website, they'll have access to this whole recording and they can download the slides from there as well. And I know Autumn had a few hyperlinks in her slides. So, once you download, you can actually visit those sites.
Perfect. Thank you so much. All right. And the rest is, I love to see the interaction. You guys have been great. We've been doing webinars all year long. And the last questions are really communications between you all. So that's fantastic. We love to see it. You guys have a wealth of information and knowledge, and any opportunity to share it is great. I don't see any other questions though. So for that, I think we are going to go ahead and, I've got one more that just came in, looks like. So we'll answer this last question and then we will probably sign off for the day. So this question is, we have a safety concern with hydrofluoric. Also, I've heard that hydrofluoric etches glass. How is the 2000 ppm hydrofluoric solution prepared?
Yeah, so it definitely does. It is caustic to glass, so you definitely want to make sure you're keeping that away from any glass material. So if you're using concentrated hydrofluoric acid, we would just recommend preparing your matrix in a LDPE or other plastic bottle. We normally recommend LDPE just because it's we found to be a really clean container material. So just make sure you're preparing those in plastic. And then as far as the safety concern with HF, I believe it's Honeywell has a lot of good information on their website about HF safety. But yeah, you definitely want to be careful if you're working with concentrated HF because it is some scary stuff. So.
Yeah, I know there are special safety precautions that we have in our lab, a little bit extra just to deal if there's any HF spills, especially on skin. So I believe it's calcium gluconate
Yeah.
mixed up that we can apply to any areas that may get some sort of contact with HF. But yeah, definitely check out those resources for safety tips. All right. So again, I want to thank you all for your time. It has been great. And if you have any follow-up questions, please feel free to contact the technical support team here at Inorganic Ventures. Thank you all, and I hope you have a good rest of your day.
Yeah. Thanks so much.